everybody. Welcome to another exciting Q&A session. Today I am joined by Andrew Cross, who is one of our research scientists doing a lot of work in quantum error correction, here to answer all of your error correction related queries. Oop, lost Andrew. One second. There we go. All right, we lost you for a second, but can you hear me again? Oh, now I see two of you.
Two of me now.
But that's okay. Two is fine. Can you hear me?
Yeah, I can hear you.
Okay.
Can you hear me?
Yes, we're good now.
Great.
All right. First question is, how does quantum error correction account for the possibility of errors after uh wait, my question disappeared. Oh, the possibility of errors after initialization and prior to entanglement, or after correction and prior to measurement?
So I can try to have a go at that. Uh, what we really want to do is do fault tolerant computing. So we want to be able to correct errors wherever they occur in the computation. And so when you say you choose an error correcting code and um, you start to write down circuits for the error correction process and for the gates and for the initialization and all those steps. Uh, you'll you'll design those operations so that uh, if a few of your physical gates or initializations or measurements fail, um, those those errors propagate to measurements that you're making of the syndrome of the error correcting code and trigger detectors that let you see them and correct them. So I think the summary is that you design fault-tolerant operations that can tolerate errors in any of the physical operations in your circuit.
Okay, very cool. How do we take readout error of syndromes into account when we are designing QECs?
It's a good question. There are a couple different ways I could answer this. If you're, I think that you've seen by now the surface code, um, and uh, if you if you measure the checks of the surface code once, those syndromes that you get are unreliable because the measurements could have failed. And if you act on them right away, it's possible that just two measurement failures, kind of far apart from each other on the surface, could cause you to apply a really big, like, wrong correction. So rather than act on them right away, you measure them again, and you measure them a few times. And in the surface code, for example, this is enough to let you look at that history of measurements and pick out measurements that are likely to be wrong and not act on those. So again, this going back to the answer to the first question, this is about starting to write down fault tolerant circuits that can tolerate mistakes in any of the operations, including syndromes. There's another part to this which is interesting, and you may come across it in your reading, which is that you can design codes so that the syndromes are also encoded, and you can measure the syndrome a smaller number of times and still correct the syndrome errors. Those go by under the name single shot or syndrome data codes. So that's another direction that you could look.
Very cool. Okay. In quantum error correction, suppose we observe an unexpected output. Um, like, for example, say we measure 0, 0 instead of 1, 0, and then we apply an X gate to correct the bit flip error. How can we ensure that this correction doesn't mistakenly invert a correct output in the future, especially if the same gate is applied again?
Yeah, I think again, this comes down to like fault tolerant design. You should be able to tolerate, you measure your syndrome, as long as a few, a small number of faults have happened. If you design the circuit well, then uh, um, let's see if I can use some other language for this. So if I imagine putting all the error correction machinery in a box, and I just think like, okay, wires go into this, qubits go into this box, I measure some syndromes, I correct, qubits come out. You want to design that box, roughly speaking, so that if, say one thing goes wrong in that box, that uh, uh, no more than like one qubit coming out is bad, something kind of like that. So that small numbers of faults lead to small number of errors coming out, which can be corrected in the next round. And yeah, in that case, if the number is really small, you don't want lots of errors happening in two adjacent boxes. That would be bad.
Mhm.
Um, but yeah, what I'm really talking about is how you design the fault tolerant operations. Um, and I guess the point is that those circuits just don't have to be perfect, and they don't always have to give you perfect outputs after the error correction is done. You just can't be too far away from the error correcting code space.
Mhm. How can we correct errors where qubits would get entangled with the external environment? Does that
Yeah,
make sense?
yeah, that makes sense. I mean,
Okay.
so uh, I mean, an example of this is a T1 error, a damping error,
Mhm.
where you could think of this as the qubit, interacts a little bit with an environment, and then that environment qubit flies away and takes some information with it. Um, and I mean, I guess this is trying to think of a concise way to explain this. The the codes are designed to, yeah, let's do it this way. The codes are designed to correct small numbers of arbitrary errors. When we learn about error correction, we learn that they correct bit flip errors and phase flip errors and bit flip errors and phase flip errors together. But those those three errors as matrices actually span the set of errors. So when an arbitrary error occurs to a qubit and we measure the checks, the error gets sort of projected onto a specific type of error, which can then be corrected. So when the qubit, whether the noise is arising because of some interaction with something or because we did an operation not quite right, it's sort of the same in terms of how we correct it. There are there are some nuances, like when you interact with something externally, is that external thing remembering something about what you've done? That's going to be harder to correct. Um, but this is the basic idea, and you can correct those kinds of errors.
What are some of the more theoretical challenges to devising new codes in to attain more error correction capabilities? Oh, yes, thank you.
Okay. I mean, there are many
Besides
of them.
many things.
Yeah. Uh, I mean, some of the things that we're currently interested in. I mean, we're interested in finding. So we're interested in finding more efficient codes, which I think you've heard about. Uh, we're interested in codes that encode more qubits, but um, where you can measure check operators with by only interacting with small numbers of qubits at a time. These are LDPC codes. Um, uh, I mean, there are. It's really hard. There are a lot of challenge. I mean, so we would like to find better codes. That's one challenge. We would also like to find other ways of applying universal gates to those codes that are more efficient than the techniques we have now. more efficient than magic state distillation or related techniques. Um, and there's been a lot of progress on that recently. Um, we would like to find faster ways of applying gates. And there are many ideas for doing this, using more transversal operations or using single shot codes, things like that. Um, yeah, there's a lot. I guess I should probably stop here.
Okay, this is kind of a fun one. So the topic of error correction is obviously very broad. Are there any books that you could recommend to study it in depth, especially things that have a focus on the modern developments in the field?
That's a good question. I don't know if I'm going to have a great
You
answer
have
though.
a lot of
Uh,
different.
I mean, for the most modern developments, I would like follow the archive and Cyrate. Um, I have, you know, books that I learned from, like Nielsen and Chuang. There's a book by Kataev, Shen, and Viali. There's a book by um, um, David Mermin. Uh, yeah, I mean, I don't. Yeah, I'm sorry, I don't have a better answer for that. Where I learn about the modern things that are happening right now is on the archive and Cyrate first, and then
Right.
other published papers.
Yeah, I think a misconception that I come across a lot is people think that the body of knowledge that researchers have accumulated in their brains mostly has come from textbooks. And I just don't think that is true, especially in the case of, more modern developments, like you were saying. By the time they make it into a textbook from a research paper, it's not so modern anymore, usually. Um, are there any error correction methodologies that are applicable to other types of qubits at the same time, besides the Josephson junction based ones? And if so, how much do they vary?
Yes, there are other. Um, I would say that, I mean, all of them are based on somewhere in the concept of encoding information into an error correcting code. Um, there are um, there are techniques based on measurement-based computing that are more suited to other to different technologies. There are codes called continuous variable codes that, for example, could encode information into oscillators. And there are schemes for designing, for encoding qubits into oscillators, um, and that they're of a different flavor. Uh, um, yeah, I mean there are other ideas like this. I think that's probably a good list to start.
Mhm. Um, how is quantum error correction tied to the work we're doing in HPC?
Uh, okay. Maybe let me answer kind of a related question, which is, where do you expect to do a lot of computing when you're doing quantum error correction? Um, and in that case, um, in addition to the quantum operations that you're applying to measure checks and to transform the state of the code as you compute, you're constantly observing this stream of measured syndromes. Um, and in many technologies, the stream is there are a lot of bits that you're looking at um, um, per microsecond, and these have to be processed in real time. That's a really important fact. Um, they have to be processed in real time so that you can keep up with the rate of the information that's coming in. And what that processor that's doing this has to do is it has to look at those measurements and make inferences about which faults have occurred and write those down and keep them up to date. And so that's a difficult problem, especially when you have hardware, I mean, such as, for example, superconducting qubits, where the clock speed of the quantum hardware is relatively fast.
Um, Why do Z rotation gates in the calibration data for quantum devices often report no error? Does that mean no Z rotations have occurred, or do Z rotations inherently not have error?
I mean, in the way that we apply Z rotation in gates physically now is by an update to a piece of classical information that has to do with the phase. And so, because that update's happening in control hardware, it really has negligible error compared to the other operations. Um, yeah.
Are we exploring hardware-based error correction, something specific that would implement certain codes, like FPGA-based supporting hardware or accelerators? Is that a viable path for quantum?
Uh, so, I mean, hardware-based error correction has a couple different meanings. What I will take this to mean is, recently we released a new roadmap. We have some devices coming out on this roadmap, and those devices are built with connectivity that is designed specifically for measuring syndromes and eventually doing gates on encoded information. And in those devices, the connections are fixed a particular way. And because of that, you might say it's hardware based in the sense that I need to use the set of connections that are available to me when I implement the code. And I like those physical connections to be as close to the ones that I want to do. I want to have when I'm doing gates because I want to try to detect errors as quickly as I can. So I don't want to have to do a lot of swap operations or anything like that. So in that sense, I think um, our view right now is that we like to design hardware that is tailored for the types of operations we need in error correction, so that those can be reliable, so that the codes can perform well.
Did I get all of the questions? Sorry, just give me a second. They keep updating. Um, I think we have reached the end of the questions, but there's a few more minutes left. So if anybody else has a few more questions, feel free. I'll give everyone just a few minutes here. Okay, here's one. If Clifford operations can be isolated in circuits, what prevents us from simply executing the Clifford portions more efficiently on a classical computer and only sending the non-classical rotations and such back to the quantum computer?
Yeah, that's a good question. In some sense, you can do this. There's a model of computing that shows up in the surface code and also in some of our recent work. It goes by the name of poly-based computing, where you're computing uh, by applying a sequence of poly measurements. Um, and when you do this, the expensive part of the computation, like you said, is when I want to do something that's not a Clifford operation, when I want to say consume a magic state and do a T-gate. Um, so in this case, what you can do is you can recompile your circuit and push all of the Clifford gates through those poly measurements. It changes the poly measurements, but all the Clifford operations get pushed all the way to the end, and they can be kind of eliminated. Uh, and what's left is the part of the computation that's non-Clifford.
Perfect. All right. Um, I'm just making sure we answered all of these. Let me see. Oh, can you please define again for us what a magic state is?
Oh, sure. Yeah. Okay. So, uh, with stabilizer codes, the easy operations to apply are these Clifford operations, and we need something non-Clifford in order to do universal computing. And turns out that basically anything that's non-Clifford is going to give us a universal gate set. Um, magic states are those are states that are not uh, that you can't get that they're not stabilizer states. They're not things that you can easily produce with Clifford operations. And more specifically, there are different kinds of these magic states. The ones you'll most commonly hear about are states that are called T states, and these are very simple. It's ket 0 plus e to the I pi over 4 ket 1, and so it's a state that you would get by creating an equal superposition of 0 and 1, and then doing a phase rotation. Um, um, a lot of the work that goes into building a fault-tolerant architecture is to try to produce these states reliably encoded in an error correcting code. And a really important result from the early 2000s is that you can start with a bunch of unreliable copies of these states and then process them using only Clifford operations and measurement and classical feedback to make to take this large number of noisy magic states and turn them into a smaller number of reliable ones. And then you can sort of iterate this process and make them more and more reliable. That's called magic state distillation.
Perfect. Um, all right. I think we have answered all of the questions. Yep. Looks like we got through all of them. So let's thank Andrew again for his time. Thank you, Andrew. Really appreciate you stepping in here and educating us all a little bit more about quantum error correction. It's certainly not a topic that I am intimately familiar with. And I know everybody in the chat really appreciates it. So go ahead and take a minute to thank Andrew, and we can close just a little bit early today.
All right. Thanks, everyone.
Great.